All right, in section 9.5, we're ready to begin our discussion on series, which is just simply the sum of the numbers in a sequence. And so we talked about sequences in 9.4. A lot of that information will become important here in 9.5 as well. And so here we go. Summation notation, or sigma notation, is what we're going to focus on first. And this is just a shorthand way of writing a big long sum out to be able to do it very quickly, and it's used with the explicit formula only. So we're not going to be using recursive formulas in this particular section, just the explicit formulas. And so we denote sigma notation. This big capital Greek letter here is called a sigma. Sum from n equals 1 to k of a sub n. And so here's a couple of things. A sub n is the explicit formula, as I said before. N is the index of summation and what term to begin with. So here I've put n equals 1. This will not always necessarily be n equals 1. It could be n equals 5 or n equals 7 or something else. But it always tells you what term number to begin with. K is what we call the upper limit, and it is what term number to end with. And I'm going to underline the word number because the most common mistake that I see is students just put the last term as the upper bound or the upper limit. We don't want what the last term actually is. We want the number of that term. So, for example, if we say that the last term is a sub 5 is equal to 20, then my upper limit is going to be the 5, not the 20. And so we're looking for the term number, not the actual term itself, whenever we put the upper limit. Okay, so just a couple of examples to hopefully help us get going here and figure out what this sigma notation means. First of all, in A and B, just some review. If I have this sequence capital A, then A sub 3 is going to be the third term in that particular sequence, and so the third term, counting them out, is just going to be 13. A sub 5 is the fifth term in this sequence, and so counting them out, you're going to get that 17 is the fifth term. And you could come up here if you wanted to and just write down which term each of those guys are. Okay, for letter C, we've got our first sigma notation problem. This is read the sum from n equals 1 to 3 of a sub n. And so what this is going to equal to is I just start by plugging in the first value for n into n. And so if I plug n equals 1 in for n, this is going to be a sub 1. Sigma then means to sum. So I'm going to put a plus, and I'm going to plug the next value for n, which would be 2, and so that's going to be a sub 2, and then I plus again because this means sum, and then I go to a sub 3, and because 3 is the upper limit, that means I'm going to stop there. And so what is a sub 1, a sub 2, and a sub 3? That would be 8 plus 10 plus 13, which I believe is equal to 31. Okay, letter D, very similar, and so here we're going to start with n is equal to 2, and so I'm going to have the second term plus a sub 3 plus a sub 4 plus a sub 5 plus a sub 6, and so we know what all of those terms are. 10 plus 13 plus 14 plus 17 plus 20, and just doing some quick mental math that hopefully is correct, I believe you're going to end up there with 74. Okay, in example 2, we want to write an expression for the sum of the series using sigma notation. And so there's a couple of things that we have to do here. The first is we have to find the explicit rule for this particular series. And so the first thing that we have to do before we can even do that is figure out what type of a series it is. And so we have two types of series that we sort of discussed in section 9.4. We have arithmetic sequences or series, and we have geometric sequences or series. So I know that arithmetic has a common difference, which means that we are adding the same number to each term to get the following terms. And geometric sequences have what is called a common ratio. And depending on which of these particular sequences we're dealing with will tell us which explicit formula to use. And so it's very important that we can identify when a series is arithmetic, meaning it has a common difference, we're adding those terms together as we go along, versus a geometric sequence which has a common ratio where we are multiplying by the same number every time. And so if you look at -6 minus 3 plus 0, probably you could figure out what the next number is. That would be +3 plus 6 plus 9. This is an arithmetic series, and so we're going to use the formula for an arithmetic explicit sequence to get our a sub n. So just as a reminder from the previous notes, here is our formula, and so we're just going to plug in and simplify this. So a sub 1 is -6, n minus 1 I'm going to leave alone, and then my difference, I'm adding 3 each time, and so that's going to give me 3 as my difference. And so I'll have -6, I'm going to go ahead and distribute my 3, and so simplified, this will be 3n subtract 9. And so now I am ready to start writing my sigma notation. We are always going to have our sums begin at n equals 1 whenever we write it in sigma notation, so that will always be n equals 1 down there on the bottom, and then I'm going to put my formula here, 3n minus 9. Now the last thing that we need to figure out is what the upper limit is going to be, and like I said, the most common mistake is that people just want to put 42 on that upper limit because it's the last term, but we need to figure out which term 42 is. And so the way that we're going to do that is we're going to set a sub n equal to the last term to find the upper limit. And so this is how it's going to be done each and every time there is an upper limit. Sometimes it'll be an infinite series, and so the upper bound will be infinity, but because this is a finite sequence, meaning it stops once you get to the term 42, we're going to find what term number that is. And so I'm going to have 3n minus 9 as my a sub n. I'm going to set that equal to the last term, which is 42, and I'm going to solve for n. And so 3n is going to equal to 51, and if I divide both sides by 3, that's going to give me n is equal to 17. And so 17 will go as my upper bound, and that is the shorthand way to write this series using sigma notation. Okay, here in letter B, once again, we needed to figure out, is this arithmetic or is it geometric? So does it have a common difference, meaning we're adding the same or subtracting the same number every time, or does it have a common ratio, meaning we are multiplying by the same number every time? And so hopefully you can identify this as a geometric series, and it has a ratio that is equal to positive a half, because each time I am multiplying by a half to get to the following term. And so that means when we find a sub n for our first step, we're going to use the geometric sequence formula. So that says a sub n is equal to a sub 1 r to the n minus 1. And so what is a sub 1? It's 1. And what is r? It's 1/2 to the n minus 1. Now, the second thing is we're going to set a sub n equal to the last term, and this is going to allow us to figure out what the upper bound is. And so I'm going to take 1/2 raised to the n minus 1 and set that equal to the last term, which is 1/128. And so now we have to revert back to when we discussed logarithms and think about how we solved an equation like this. And you don't necessarily have to use logarithms, but what I'm going to do is I'm going to find the like base. And so on both sides, the like base is 1/2. The left-hand side is already in terms of 1/2, and so I just need to figure out what power of 1/2 is 1/128. And it turns out that it is the 7th power of 1/2. If you were to plug in 1/2 to the 7th, you would get 1 over 128. And so now I'm ready to drop the bases, set the exponents equal to each other, and get that n is equal to 8. And so that is going to be my upper limit in my sigma notation. And so now I'm ready to write my answer. The sum from n equals 1, remember I said that it would always be n equals 1 on the bottom, 1/2 to the n minus 1. I didn't write the 1 in the front because multiplying by 1 doesn't do anything, and then the upper limit will be 8. Okay, one more example just for extra practice. So take a look at this series, see if you can determine if it is arithmetic or geometric, and hopefully after you take a look at it for a second, you realize that this is arithmetic because it has a common difference of positive 3. And so the first thing I'm going to do is I'm going to find my a sub n, and so reverting back to that arithmetic formula that we used back in example A, we're going to plug in what we know. So I know that the first term is 4 and that the difference is 3. And so now I'm ready to distribute. That's going to give me 4 plus 3n minus 3, which will give me 3n plus 1. And so now we want to find our upper limit. That is step 2. And so that means we're going to take our formula that we just found and set it equal to the last term. And so this will be subtracting 1 on both sides. 3n is equal to 36. Dividing both sides by 3 will give us an upper limit of 12. And so now the sum from n equals 1 until 12 of my formula, 3n plus 1.